EC 201, lecture 42. Today we were at this point where we were trying to investigate the behavior of a closed loop negative feedback system, where we understand that the forward amplifier A of S cannot respond instantaneously to its input. It takes some time, and that's because of any practical forward amplifier is associated with parasitic capacitances which basically slow down the response of the circuit. Simply at the block level, if this is V in and this is V out, we saw that if A of S was a single pole amplifier whose gain was given by A naught divided by 1 plus S by omega P, then we said that the closed loop gain which is V out of S by V in of S is given by 1 over F times A naught F by 1 plus A naught F times one by 1 plus S by omega P times 1 plus A naught F. So this is the gain we would have expected if the forward amplifier had no pole at all. And this is the DC gain of the closed loop system. This is the bandwidth of the closed loop. And we see that the closed loop bandwidth is approximately omega P times A naught F, and yesterday we saw why this expression makes sense. In the beginning it might be a little puzzling because the open loop bandwidth is only omega P. So beyond omega P the gain is falling off. However, the closed loop bandwidth is omega P times A naught F, and that makes sense because the closed loop gain is of the form 1 over F times AF by 1 plus AF. The closed loop gain will not deviate from its DC value until this number AF becomes so low that AF by 1 plus AF deviates significantly from unity. Typically we think of amplifier as being completely useless beyond the 3 dB point, but in this context you see that the forward amplifier still works as long as the gain has not yet reached about unity. Is that clear? At what frequency does the forward amplifier have a unity gain? Okay, it's approximately A naught omega P, but then we know that the closed loop gain is not forward amplifier by forward amplifier plus 1, but forward amplifier times F, which is the loop gain, divided by 1 plus loop gain. So when the loop gain falls to about 1 is when the feedback action is roughly dead. If the forward amplifier is a single pole system and the feedback network F constant, then the closed loop system is also a single pole system. Can you comment on the stability of the closed loop? If you have a linear system, when is a linear system stable? When the poles are all on the left half S plane. So are the poles of the closed loop system in the left half S plane or in the right half S plane? They are all in the left half S plane. So the closed loop system is stable. And is there any condition on A naught that needs to be satisfied for the closed loop system to be stable? look at this expression and tell me, as long as you make sure that the feedback is negative feedback, and which basically means that A naught and F must be positive, then you see that this closed loop system is stable unconditionally. When I say unconditionally, it means for all values of A naught. Is that clear? I mean, this is a trivial statement, but as we go along, we'll see that things are not quite as trivial as we get to higher order systems. And the closed loop bandwidth is approximately omega p times A naught times F. Okay? You understand? And one useful way of thinking about this number is the following. Can anybody comment on this number omega p times A naught? A naught omega p is nothing but the gain bandwidth product of the forward amplifier. And this gain bandwidth product of the forward amplifier would also be the closed loop bandwidth if the feedback factor F was unity. Now, if the closed loop system was designed to have a gain of say 5, what do you think the closed loop bandwidth will be? So, if the closed loop system was designed to have a DC gain of 5, it means that F will be 1 by 5, which means that the closed loop bandwidth will be, it will be 1/5 of the gain bandwidth product of the forward amplifier. And you know that an operational amplifier is basically doing this entire, its job is to do this. We have seen this already. On an op-amp data sheet, you will often find this number, which is, they quote the gain bandwidth product of the op-amp. For example, the 741, which is a very, very popular operational amplifier, has got a nominal gain bandwidth product of 1 megahertz. That basically means that if you configure it, if an op-amp has a gain bandwidth product of 1 megahertz, it means that if you build an amplifier like this, what is the closed loop gain? The closed loop gain is 1. So what is the closed loop bandwidth now? This circuit will have a bandwidth of 1 megahertz. Now, if I did this, what is the closed loop gain? The closed loop gain is 2, the bandwidth will be is about 500 kilohertz. As we said yesterday, we saw that from a single stage, it's not possible to get very large gain. So, even though we like A naught to be very, very large, that's not possible because of physical constraints on the devices, and in which case, one logical way of getting more gain is to cascade several stages. So now let's repeat the same exercise when we had 2 stages in the amplifier. the same A of S, the same F. However, A of S is now of the form A naught divided by 1 plus S by, say, omega P the whole square. A two-stage design for the forward amplifier. The hope is that the A naught you can get here is considerably higher than what you could get with a single stage. What would be the closed loop gain now? One thing, of course, is you can go and do the maths. A lazy man's way out is to notice the following, that this is 2s by omega p plus s square by omega p square. So instead of going through the whole circus again, all I could do is replace s by omega p in the earlier expression with this 2s by omega p plus s square by omega p square. In the earlier expression for the single pole forward amplifier, the closed loop gain was 1 over f times A naught f by 1 plus A naught f times 1 over 1 plus s by omega p times 1 plus A naught f. Now all that we have to do is replace s by omega p with 2s by omega p plus s square by omega p square divided by 1 plus A naught f, which I conveniently approximate as 1 over f divided by 1 plus 2s by A naught f omega p plus s square by omega p square times A naught f. And how does this approximation come about? The reasoning behind making this approximation is that A naught f is much larger than 1. Clearly, the forward amplifier is a second order system. The closed loop system is also of second order. Can you comment on the stability? When is the system stable? When both the poles are in the left half S plane. So if you have a second order denominator, the poles will always be in the left half S plane if the coefficients are all of the same sign. Clearly A naught is positive, so this, and omega P is positive, F is positive, so this is positive. So is this. The stability of the second order closed loop system is also unconditional. A general second order system can be written in this standard form. It's called S by omega naught Q plus S square by omega naught square. So where do you think the roots of this polynomial lie? The roots of this polynomial are nothing but the poles of the system. So where do the roots lie? What are the roots? I mean, what are the locations of the roots rather? Yeah, it depends on Q. Can you please tell me what the locations are? It depends on Q and it depends on omega naught. Minus 1 by 2Q plus or minus J square root of 1 minus 1 by 4Q square. If I plot the locations of the roots on the Laplace plane, So if I plot S by omega naught rather than S, so that the scaling factor omega naught is removed. When Q is very, very small, what do you think happens to the roots? If Q is very small, both the roots are real and are on the negative real axis. Small q, 2 real poles. When do the poles start to become complex conjugate? So for q is equal to half, you get, that's the point at which you get 2 equal roots. And for q greater than half, you get complex conjugate roots. As q tends to infinity, what happens? The roots are on the j omega axis. So in general, if I had a q greater than half, the roots would be complex conjugate in this fashion, and the abscissa would be 1 over 2q, this distance, and this distance would be square root of 1 minus 1 by 4q square. Does it make sense? So as the q becomes larger and larger and larger, what do you think happens to the impulse response of the system? 1 over d of s. D of s is this quadratic. What happens as the q becomes larger and larger? What happens to the poles? The poles move closer and closer to the j omega axis. So what if you go and whack the system, what will happen to the output? How will the system respond? Have you experienced this phenomenon in real life before? So how many of you have taken a Chennai bus on a Chennai road? So every time you hit a pothole, what happens? If the shocks of the bus are, not doing their job properly, what happens every time you go or your bike for that matter? There's a pothole on the road, the shock absorbers are not sufficiently lossy, or they don't damp your stuff very well. If you just have the spring, if whatever dissipative material in the shock absorber is screwed up, what do you think will happen? You hit a bump on the road and you keep jumping up and down like this. So this is because the quality factor of this system, which is the mass spring system that you are part of, has got a quality factor which is the poles are very close to the j omega axis. And what will be the frequency of these ringings? Look at the Laplace plot and pole positions and tell me. If the poles sit on the j omega axis, what would you expect? In respect, if you touch the system, it will go on ringing like this. And the frequency of the ringing is the radian frequency of omega naught, so the time period is 1 by, it's f naught, which 1 over f naught, which is omega naught by 2 pi. For an amplifier, the Q of the denominator quantifies the losslessness of the system . So in circuit literature, it's often called Q. The reason for calling it Q is Q stands for the quality factor. All this comes from trying to make LC networks, and it turns out that in practice the LC networks, L's and C's are lossy. So even though you put a pure LC together and excited the system, you will find that beyond a certain amount of time, the energy is lost in the resistors or the loss of the system. So the oscillations will die down, okay, after a sufficiently long time. And how long the oscillations take to die down are an indication of course, the damping. But if the oscillations last for a long time, does it mean that it's less lossy or more lossy? Less lossy. In other words, the quality of the inductor and the quality of the capacitor is good if the oscillations persist forever. So this is called the quality factor. And since there are two poles, this is a pole pair. So any pole pair is always associated with a quality factor. A high quality factor pole pair means that the impulse response of that system will last for a very, very long time. In the control system literature, it is often common to denote 1 over Q as 2 times some fancy Greek symbol which I can never remember what it is called. It's called the damping factor. So this Q is called the quality factor, and this omega naught is called the natural frequency. And another thing to remember is that a high quality pole pair means that the ratio of the imaginary part of the root to the real part of the root is approximately equal to 2Q. A high quality pole pair will have roots which have a significant imaginary part. And of course, with Q becomes infinity, the real part becomes 0. Alright, now let's get back to our particular example. So this is the closed loop gain. So what is the natural frequency of this second order denominator? Omega naught is omega p square root of A naught f. And what is the quality factor of the second order denominator? Omega naught times q is A naught f omega p by 2, which implies omega p times square root of A naught f is A naught f omega p by 2, q times this, which means this goes away. Q is simply A naught f square root divided by 2. You understand? And what did we say about A naught f? We want A naught f to be very large. And that implies the closed loop system is stable and the quality factor of the poles is very, very high. And what does this physically mean? Is this a good thing or a bad thing? This was the Alright, this is the input to an amplifier. It's a step. This is time. And assume that the closed loop gain is 1, so that the output eventually will settle to the same value as the input. Okay. So now if the quality factor is very low, that is the what do you call, the roots of both real, what do you think the response will look like? It will be a sum of exponentials, so very low Q. The Q starts becoming larger and larger, what do you think will happen? As the Q starts to become higher, it starts to do this, then it starts to do this, and the Q becomes very, very, very large, what do you think will happen? The Q becomes very large, then you understand? So imagine you are going on a bumpy road and the shock absorber is screwed up. So you hit a pothole and you are jumping up and down and up and down and up and down, and then you hit the next pothole and again you are jumping up and down and up and down. The question now is that, do you want to have a large Q or a small Q? A very high Q is certainly not something that you want, because the amplifier keeps ringing forever. If Q becomes infinite, for example, this will become, it will keep doing this. Note that in all these cases, the average value of the output is still correct. The average value of this waveform is 1, and so is this waveform. After a very long time, all these asymptotically approach 1. But the time taken for them to approach 1 will be very, very different. This, for example, will never approach 1. Of course, having a very low Q is also not very good, because the response is still very sluggish. What you want is a Q which is, when the poles simply just become complex conjugate, is when you have something which responds rapidly and just dies down like this. So now let's get back to our situation. We want A naught F to be very large, but the moment you close the loop around such a system, you find that the closed loop quality factor of the poles is very, very large. That means you touch the amplifier and the output, it goes on ringing at its natural frequency for a very, very long time. A rule of thumb is that if you look at the response of a second order system and you want to find the Q, a very good first estimate of finding the Q is count the number of cycles you can see visually. Okay. So if you can see 10 cycles, it means that the quality factor of the second order system is about 10. In this thumb rule, if you want to make A naught F 10 power 4, then the quality factor of the closed loop system is 100, which means that you just excite the system and it keeps ringing 100 times before it eventually settles. That's obviously not a very good state of affairs. Okay. So even though the second order system is unconditionally stable, you find that the quality factor is too high. So the story so far is we tried a first order system, everything is great, except that we just can't get the high enough A naught. Then we said, okay, one way of getting high enough A naught is to cascade two identical amplifiers, in which case you will be able to get the large A naught, but the moment you close the loop, the quality factor of the closed loop is very, very large. Okay. So the next thing is to say maybe the third order system will help us. In which case, just as we proceeded before, A of S will be denoted as A naught divided by 1 plus S by omega P the whole cube. The reason for choosing the same omega P is just to simplify analysis, and it's not too far away from the truth. So what happens now with the closed loop system is simply 1 plus 3s by omega P plus 3s square by omega P square plus S cube by omega P cube. So all I have to do is replace S by omega P in the expression for the first order system by this beast here. The closed loop gain is simply 1 over F times A naught F by 1 plus A naught F divided by 1 plus 3s by omega P plus 3s square by omega P square plus S cube by omega P cube times 1 over 1 plus A naught. So the denominator of this system is 1 plus 3s by omega P times 1 plus A naught F plus 3s square by omega P square times 1 plus A naught F plus S cube by omega P cube times 1 plus A naught F. The first thing to do is to obviously figure out if the loop is stable or not. So any comments on how I might be able to figure it out? So to avoid carrying over S by omega P everywhere, I can actually find the roots of d of S by omega P, which is a polynomial with I'll multiply the whole equation by 1 plus A naught F. Okay, we're trying to figure out where the roots of this beast lie. The suggestion is I multiply the equation by a constant, so obviously the roots mustn't change, the location of the roots can't change. So 1 plus A naught F plus 3s square plus S cube must have the same roots as this equation. Please note that all the coefficients are positive. There must be one real root for sure, the third order equation, and not necessarily two complex roots, but if there are complex roots, they will occur in complex conjugate pairs. Okay, how will you approach? Look at this and say this is 1 plus S the whole cube must be equal to minus A naught F. So this must be 1 plus S must be equal to A naught F the whole part 1/3. So the roots must be minus 1 plus minus A naught F the whole part 1/3. We will take a simple example. A naught F is say 8. What happens? There must be 3 roots. A naught F is equal to 8. What are the 3 roots? Can you please calculate and tell me? Minus 1, minus 2, which is equal to minus 3. What else? Pardon? Minus 2, j pi by 2. Minus 2. It's minus 1 plus minus 2 e to the j 2 pi by 3. The other one? Minus 1 minus 2 e to the 4 pi by 3. Okay, can you find the real and imaginary parts of these numbers, please? What are the real parts of S2 and S3? Okay, figure